Hi everyone, in this video we will show that the differentiability implies the continuity of functions. By the end of this block and watching this video, you will be able to analyze the relation and difference between differentiability and continuity. If a function is differentiable at a point, we believe that the graph of the function is somewhat smooth there, so it is very natural to guess that f must be also continuous at that point. So in this video, we will find a mathematical justification of that observation. Let's review the definitions of differentiability and continuity first. We say a function f is differentiable at x equal a if the derivative f prime of a exists. Let's list all the properties that are implied by this statement the derivative exists. First of all, it means f of a exists. That is to say, a is in the domain of f. And also, the limit of f of a plus h minus f of a divided by h exists as h approaches 0. Now the continuity. A function f is said to be continuous at x is equal to a if f of a is equal to the limit of f of x as x approaches a. Again, let's list all the properties that are implied by this identity. First of all, it means f of a first exists. That is to say, a is in the domain of f. And the limit of f of x as x approaches a also exists. Finally, these two values, f of a and the limit of f of xa, is equal to each other. Let's come back to our main statement that we want to justify. If a function f is differentiable, then the function is also continuous. So since f is differentiable, we know that function f satisfies the two properties. So this part is called the hypothesis of the mathematical statement. And now the conclusion that we need to prove is that f is continuous. That is to say, we have to show the three properties to be satisfied. Okay, so one more time. The hypothesis is what we already know. So we know f already satisfies these properties. Now we need to show that f satisfies these three other properties. As we see, the first property of the conclusion is already satisfied, checked. Now to show the second and the third properties, let's go back to the last property of the hypothesis. The limit of the fraction exists. Now let's notice that the limit as h approaches 0, the limit of the denominator is 0. So to have the limit of the whole fraction exists, we must have the limit of the numerator is also 0. Because otherwise, we cannot have a finite value for the limit of the fraction. Now let's look at the limit of the numerator. As h approaches 0, the second term, minus f of a, is fixed as minus f of a. So to have the limit of the difference 0, the limit of f of a plus h must be f of a. Now let's replace h by, let's replace a plus h by x. Then as h approaches 0, x approaches a, so the limit of f of x is equal to f of a. So this final conclusion automatically shows that the limit of f of x as x approaches a exists, and f of a exists, we already know, and then they coincide to each other. So we completed these two properties. So we found a very close connection between the differentiability and continuity. So if we draw a circle for the set of all continuous functions, we find out that the set of all differentiable functions must be a subset of the set of continuous functions. You may wonder if they are equal to each other, which means, is it true that the continuous function is always differentiable? And the answer is no, because in the outside of this subset, there are actually a lot of continuous functions that are not differentiable. For example, the absolute value function. Right? So this is the graph of the absolute value function, and this is the graph of its derivative. And as we see, f prime of 0 does not exist. So f is not differentiable everywhere. Okay, here are two interesting questions that you may want to think about. Is the derivative of a differentiable function always continuous? Can you find a counterexample? The second question says, can you find a function f whose derivatives, including f, are all continuous? Thank you.